Hi and welcome to this video where I'm going to be discussing how you can evaluate the relative conductivity of different solutions, particularly relating to weak acids and weak bases and ionic substances. Okay, so first some general guidelines. First off, electrical conductivity is dependent on the presence of charged particles in the solution. Now, if you do electricity and physics, you will know that those charged particles are electrons. And if you think about structure and bonding and that side of things, then yes, anything that has freely moving electrons can conduct electricity, of course. But when we talk about ionic compounds, ions are also considered charged particles, and when those ions can freely move, then electrical conductivity can occur. Okay, so that's the first thing. So electrical conductivity depends on the presence of charged particles in the solution, and the more charged particles that you have, the greater the conductivity will be. So compounds that have good electrical conductivity are going to be ones that completely dissociate in water, such as strong acids or bases, or completely dissolve in water. Now, I've used those two terms where dissolving means to break up into ions and dissociate means to react with water to form hydronium or hydroxide ions. And now those terms are used fairly interchangeably in different textbooks. I've just used those two words to kind of differentiate between these two concepts. Okay, so things that like sodium salts, ammonium salts, etc., they will completely dissolve in water, so it doesn't matter. Sodium chloride, if I add it to water, will break up to form sodium ions and chloride ions completely. Not all salts will do that. So the things that have poor electrical conductivity, you've got things that only partially dissociate in water, so in terms of weak acids and weak bases particularly, and things that are only sparingly soluble. So if you think about all those sparingly soluble salts that we talk about in the first section of this topic, all of those are going to have relatively poor electrical conductivity because they do not produce large amounts of charged particles in that solution, especially compared to so-called soluble salts. Okay, now, so that's the basic idea. Some details. Okay, so strong acids and bases will always have good electrical conductivity because they completely dissociate in water. And often the question conflates conductivity and pH. And so typically, and this is dependent on concentration, so it's not always the case, strong acids and strong acids will typically have pHs between 1 and 3 depending on the concentration, and strong bases between 12 and 14. Now, that's not to say that you can't have a strong acid with a pH of 5. You can. It's very dilute, so you do have to understand the concentration as well. I'm just saying, in general, most of the strong acids and bases you're going to deal with will have pHs in that range. In contrast, neutral salts, like sodium chloride, so things that are neutral, will also have very good conductivity because they completely dissolve in water, but they will have a pH of 7 because they're neutral. They don't form hydroxide or hydronium ions in solution. Weak acids and bases, so things like ammonia, hydrofluoric acid, amines, carboxylic acids, etc., will have a poor conductivity because they only partially dissociate in water. Only a very small amount of it reacts with the water to form ions. And again, depending on their concentration, pH is sort of in that not particularly high or low range. It's a wee way away from neutral, but it's not that far away from neutral. Having said that, like I say, it does depend on concentration. And finally, we have our acidic or basic salts. So things like ammonium chloride, sodium ethanoate, those sorts of things. They will have excellent electrical conductivity because when you add them to water, they completely dissolve to form those charged particles. So you've got lots of charged particles in solution, but they won't have a very high or low pH. Their pH is just off neutral. And that is because they're usually very weak acids or bases. So the sorts of things you might expect to see and this is an exam question from 2018, was to evaluate the electrical conductivity of ethanoic acid and ammonium chloride solutions, including relevant equations. And the previous part of this question told you that those solutions were of the same concentration. So that's another little trick to look out for, because obviously if you've got different concentrations of solution, then that can change again how many charged particles you get. So this is the sort of answer. You'll notice that I do have equations in there because the question quite clearly says you must use equations. So first off, a simple statement. The solution of ammonium chloride will have a better conductivity than a solution of ethanoic acid of the same concentration. This is because the ammonium chloride dissolves completely in water, forming a high concentration of ions, and these ions or charged particles are able to conduct electricity. So what I've done here is I've made a statement saying which one is going to have the better conductivity. I've defined the requirement for electrical conductivity, which is the presence of charged particles, and I've stated why ammonium chloride has a lot of charged particles, supported with that equation that you can see there. And you'll see that I've got a rightward facing arrow, just a straight arrow, to show that all of the ammonium chloride is going to break up to form ammonium ions and chloride ions. Now what I should also have in there is state symbols. So solid ammonium chloride makes aqueous ammonium and aqueous chloride ions. In contrast, when ethanoic acid is added to water, a small amount dissociates to form charged particles, but the majority of the ethanoic acid does not dissociate. And again, I've got an equation, this time with an equilibrium arrow, showing that you've got some charged particles, but not that many. Thus, because the solution of ethanoic acid has less charged particles than the ammonium chloride solution, it will have poorer electrical conductivity. So again, relating it right back to the question. Evaluating the electrical conductivity, I've stated at the start, I've stated at the end. I've given reasons, and I've got equations to support my answer. So just think very logically about what's happening in your solution, and you will again find that those answers come pretty obviously, as long as you can remember some basic things like the definition of what leads to conductivity and so on. Okay, so this ends this section on acids and bases. The last two bits that we really need to go through, three perhaps, are around buffer solutions, titration curves, and indicators. And I hope to see you when we come back to those next. Bye.